Okay, welcome to the deep dive. Today we are going deep on database indexing, and this is really for those of you out there who are prepping for those senior software engineer technical interviews.
Yeah.
I mean, it's one of those topics that seems to come up all the time, and we've got a ton of material to work through here. So our mission, if you choose to accept it, is to make sense of all these different indexing structures.
Yeah.
What they are, why they matter so much, and how do you even start to think about choosing the right one for your system. It's like a crash course for interview success, basically.
Absolutely. We're going to break it all down, look at all those, those trade-offs, all those little details that can really trip you up, and how those decisions play out in the real world. So we're going to start with the basics, the key value indexing, and then we're going to go dupper, right? Multi-dimensional fuzzy indexes, in-memory databases, the whole 9 yards. So you can walk into that interview and really impress them.
All right, so let's start unpacking all this. Key value indexes, right? That seems like the most fundamental concept. It's that direct mapping. You got a key, and it points you right to the value. Super simple.
Right.
And like in the context of a relational database, I guess it's kind of like your primary key, right? Give you that unique identifier for a row.
Yeah, exactly. And then in other types of databases, NoSQL databases, it's that unique ID for a document or whatever it is that you're storing.
Right. So it's basically that unique ID to quickly retrieve that piece of information, I guess.
It's the fastest way to find that one piece of information.
Makes sense. So, building on this, we have secondary indexes. Now, those seem to be important when you have more complex data retrieval needs. Like, let's say you have a relational database and you want to do an efficient join. It's that secondary index on like the customer ID column that lets you quickly find all the orders associated with that customer. Otherwise, you'd be stuck scanning the entire table, right?
Right. It's all about finding related information across all your data. Like, let's say you want to find all the activity for a specific user, right? You can use those secondary indexes to quickly pull that together from different parts of the database. Without those, performance just goes out the window.
Yeah, you're stuck with these table scans. And no one wants that, right?
Yeah.
So how do these secondary indexes actually work? I mean, what's going on under the hood?
So the interesting thing is these secondary indexes are often built using the same basic structures as those key value indexes. The big difference is with secondary indexes, the keys don't have to be unique.
Right.
Like you could have multiple orders with the same customer ID.
Right.
So there's a couple of ways to handle that. One is you can just store a list of all the row identifiers that match a given key. Essentially, it's just a list of pointers.
Okay.
The other way is to just make the key unique by adding on the row ID. So even if you have multiple rows with the same value, the index entry becomes unique because you got that extra identifier.
Makes sense. So it's essentially just expanding on that key value concept to handle those more complex relationships. And I guess both B trees and LSM trees can be used to implement these secondary indexes, right?
Absolutely. Yeah. It just depends on your workload, what you're optimizing for.
Yeah, if you need those fast reads or if you're doing lots of writes. All right, so now we've got our index key, right? And it's pointing to either a list of locations or this augmented entry. Now, where does the actual data live? I've heard about storing the entire row data within the index itself, or you can just store a pointer. What are the differences there?
Yeah, that's a good question. So with an index, the key is what you search on, but the value that's associated with that key can be either the entire row of data or just a reference to where that row is stored. So if it's just a reference, it usually points to a separate storage area. It's often called a heap file. Now, the big advantage of that heap file approach is that it reduces data duplication, right? Because if you've got, 5 secondary indexes on a table, all of those indexes just contain a pointer to the same copy of the data in the heap file.
Oh, so it's basically a way to save space, right?
Yeah.
So you don't have the data copied all over the place.
Yeah, exactly.
But what happens when you need to update the data? Like especially if the size of the data changes.
Yeah, so that's a really good point. If you update a value and then the new value is not bigger than the old one, you can usually just overwrite it in place in the heap file. But if the new value is bigger, then you might need to move it to a new location in the heap file where there's enough space. And when that happens, all of the indexes that pointed to that old location need to be updated.
Oh, so there's a bit of a performance hit there potentially, right?
Yeah, because you have to update all those pointers. Alternatively, you could leave a forwarding pointer at the old location. So it's like a little sign that says, hey, the data's moved over here.
Okay, so there's definitely some complexity and some trade-offs there.
Okay.
So that brings us to clustered indexes, right? I think this is where the actual row data is stored directly in the index structure itself, right?
That's right. So with a clustered index, the index is the data. It's all together in one place. So the big advantage here is read performance.
Right.
Because when you find the key in the clustered index, you've already found the data. You don't have to go to a separate location to fetch it. Like in MySQL's InnoDB storage engine, the primary key is always a clustered index.
And in SQL Server, you can define one clustered index per table.
Right, exactly. And the key takeaway here is it's great for read speed, but there's a trade-off, right?
Because if you're storing the data directly in the index, I imagine it takes up more space, right?
Yeah, absolutely. You need more storage. And write operations can be a bit slower because the database has to, maintain the order of the data within the index.
Right, so there's more overhead for maintaining that structure.
Exactly. And it gets even trickier when you start talking about transactional consistency because, you've got data duplicated in the index. So the database has to make sure that all those copies are updated correctly.
So it's not a free lunch. There's definitely trade-offs.
Yeah.
But it sounds like it can be really beneficial for those read-intensive applications.
Absolutely.
Now, what about covering indexes? I think I've heard these called indexes with included columns. Is that right?
Yeah, that's right. And a covering index tries to find a middle ground, right? It's an index on a specific set of columns, but it also includes copies of other columns from the same table right there in the index. So for certain queries, you can get all the data you need just from the index. You don't even have to go to the main table. So the index it's covering the entire query.
So it's kind of like pre-computing the answers to certain questions, right?
Yeah, exactly. And storing those answers directly in the index.
So it's like, hey, we know people are going to ask this question a lot. Let's just put the answer right here.
Yeah, exactly. But you don't want to make the index too big, right? Because then it becomes less efficient.
Right. It's all about trade-offs. And speaking of trade-offs, let's talk about querying across multiple columns at the same time. I mean, so far we've been talking about single columns, but in the real world, you often need to query based on a combination of columns, right?
Yeah, absolutely. And that's where multi-column indexes come into play.
Right. And I remember learning about concatenated indexes, where you essentially combine multiple fields into a single key. It's kind of like a phone book, right? You sort by last name and then first name.
Yeah, that's a great analogy. So with a concatenated index, you can efficiently find everyone with a specific last name or everyone with a specific last name and first name. But if you only know the first name, then the index isn't very helpful.
Right, because the data is primarily sorted by that first column, that leading column.
Yeah, exactly.
So the order in which you define those columns in the index really matters. But what if you don't know the order ahead of time? Or what if you need to do like a range query across multiple columns at the same time? Like think about finding all the restaurants within a certain area on a map. You're essentially doing a range query on both latitude and longitude.
Yeah, that's a great example. And that's where multidimensional indexes become really important.
Right, and especially for things like geospatial data.
Exactly. So if you were using a standard B tree or LSM tree index, you'd have to do separate queries for latitude and longitude and then combine the results. And that can be really slow, especially if you have a lot of data.
Right. So multidimensional indexes help you avoid those expensive filtering operations.
Yeah. There's a couple of different techniques. One is to use what's called a space filling curve. So you basically transform the multidimensional coordinates, like your latitude and longitude, into a single one-dimensional value. And then you can just use a regular B tree to index that.
Oh, okay. So it's kind of like a mapping function, right? You're taking those multidimensional coordinates and squashing them into a single dimension.
Yeah, exactly. And that lets you use those well-known indexing structures. But more commonly, people use these specialized spatial index structures like R trees.
Okay.
And those are specifically designed to handle those range queries in multidimensional spaces. So like PostGIS, it's a popular extension for PostgreSQL. It uses R trees for its spatial indexing.
So you don't necessarily need to know the details of how those work, but it's good to know that they exist.
Yeah, just be aware of them. Yeah.
Right. And multidimensional indexing isn't just limited to maps, right? I mean, I've seen examples where it's used for things like searching products based on color ranges, or even for querying weather data based on date and temperature ranges.
Absolutely. You can use it for anything where you need to query across multiple, independent attributes. So like in your product search example, you could have a three-dimensional index on those RGB color values.
Yeah. Okay.
Or in your weather database, you could have a two-dimensional index on date and temperature.
Right.
So instead of doing separate queries and then combining the results, you can just do one query that targets the specific range that you're interested in, and that can be a huge performance win, especially for those large data sets.
Makes sense. And there are even specialized database systems that use these techniques, right?
Yeah, absolutely. There's HyperDex, for example.
Okay, cool. So far we've been talking about exact matches, right? Like we know exactly what we're looking for. But what happens when we need to search for something that's similar, but not necessarily identical? Like what if the user makes a typo?
Right.
Or what if they're looking for a broader concept? That's where full text search and fuzzy indexes come in.
Yeah, that's right. So all the indexing strategies we've talked about so far assume that you're looking for an exact match. But in the real world, you often need to be a little more flexible.
Right.
And full text search engines they're designed to handle that. So they can understand synonyms, different grammatical forms of words, and even the proximity of words to each other.
And to handle those typos, I know that tools like Lucene can search for words that are within a certain edit distance.
Yeah.
Right.
Yeah. And edit distance is basically the number of single character changes it takes to transform one word into another. So it's like insertions, deletions, substitutions.
Okay.
And under the hood, these systems often use these data structures that are similar to as stables for storing their term dictionary. So they have this small in-memory index that helps them quickly find the relevant sections within that larger, sorted dictionary file on disk.
Right.
And in Lucene's case, that in-memory index is often a finite state automaton, which is kind of like a tri-data structure optimized for prefix searching. And you can even transform that automaton into a Levenstein automaton, which can do these efficient fuzzy searches based on edit distance.
So it's all about finding those similar words efficiently, right?
Yeah, exactly.
And there are other techniques for fuzzy searching, right? Like I've seen things about, document classification and machine learning being used.
Yeah, absolutely. So document classification can help group several documents together, and machine learning can be used to understand those semantic relationships between words.
Yeah.
So if you really want to dig into those advanced techniques, check out some textbooks or research papers on information retrieval.
Right. All right, so we've covered a lot of ground here. We've talked about all these different indexing structures.
Right.
And most of them they're really designed with disk-based storage in mind. But what happens when we can keep most or even all of our data in memory?
Yep.
That's where in-memory databases come in.
Right. And this is becoming more and more important as RAM gets cheaper and data sets get bigger.
Right, because traditional disks, they're great for durability and they're relatively cheap, right? But they're also slow.
Yeah, exactly. And in-memory databases try to avoid those limitations by keeping the primary working set of data in RAM.
Now, I know there are these in-memory key value stores like memcached, and those are mainly used for caching. So the idea is that if you lose the data on a restart, it's not the end of the world. But there are also in-memory databases that are durable.
Yeah.
So how do they achieve that? I mean, how do they make sure that the data doesn't disappear if the power goes out?
Yeah, that's a really important point. And these durable in-memory databases, they use a variety of techniques to ensure data persistence. So they might use specialized hardware like battery-backed RAM, or they might log all the changes to disk, or they might take, periodic snapshots of the in-memory state and write those to disk.
Okay.
Or they might replicate the data to other servers. And even with those disk interactions, the key is that the primary data access, both reads and writes, happen in memory. So you still get that speed advantage. The disk is mainly used for persistence and for, operational things like backups and disaster recovery.
So it's still considered an in-memory database even if it interacts with disk.
Yeah, exactly. It's all about where the primary data access happens.
I've heard of in-memory relational databases like VoltDB, MemSwell, and Oracle Timestamp, and they all claim these huge performance improvements. But how is that possible? I mean, even with traditional disk-based databases, the operating system caches disk blocks in memory, right?
Yeah, but the performance advantage of in-memory databases isn't just about avoiding disk reads. It's also about avoiding the overhead of encoding and decoding those in-memory data structures into a format that can be written to disk.
Okay, so it's like a translation layer, right?
Yeah, exactly. And traditional databases have to do that translation all the time, but in-memory databases can just work directly with their optimized in-memory representations.
So it's like cutting out the middleman.
Exactly.
And I've also noticed that in-memory databases seem to be a lot more flexible in terms of the types of data structures that they can support.
Yeah, absolutely. Because you don't have those constraints of disk-based storage,
Yeah.
you can implement those complex data structures much more efficiently. So for example,
Mm.
Redis provides interfaces to things like priority queues sets and sorted sets.
Okay.
And trying to implement those efficiently on disk, it would be a lot harder and it would probably involve a lot of trade-offs.
Right. It'd be really complex.
Mm.
And I even came across some research on these anti-caching techniques for in-memory databases. And that sounds kind of counterintuitive, right? Because the whole point of an in-memory database is to keep everything in memory. But the idea is to handle those data sets that are actually larger than the available RAM.
Yeah, it's kind of a mind-bending concept, but the basic idea is that you extend those benefits of in-memory processing to larger data sets by swapping out the less frequently used data to disk. But you do it at a very granular level. So you're typically swapping out individual records instead of entire pages.
Okay.
And the key is that the indexes still need to be in memory so you can still do those fast lookups.
So you're still getting some of the benefits of that in-memory processing, even
Yeah.
if not everything can fit in RAM.
Yeah, exactly.
And finally, we've got non-volatile memory, NVM.
Right.
And this is kind of a new technology that has the potential to really change the way we think about storage.
Yeah, it's still early days, but it has the potential to combine the speed of RAM with the persistence of disk. So that could really shake things up in terms of how we design these storage systems.
All right, well, that's a whirlwind tour of database indexing.
Yeah.
I mean, we covered a lot of ground here. We talked about key value indexing, secondary indexing, multi-column, multi-dimensional, fuzzy indexing, and in-memory databases.
Yeah, we hit all the major points.
And for anyone who's preparing for those senior software engineer interviews, this is really important stuff. I mean, you're going to get questions about system design, database optimization, performance troubleshooting, and indexing it's at the heart of all of that.
Yeah, absolutely. It's one of those fundamental concepts that you really need to understand.
So as you're preparing for those interviews,
Hmm.
think about your past projects. Think about the systems you've worked with and ask yourself, could you have used a different indexing approach?
Yeah.
Would that have made things better?
Yeah. And as those in-memory technologies become more and more accessible, how is that going to affect the way we design and build applications in the future?
Right. Those are good questions to be thinking about.